sweet, it's unplugged. Alright. Hi everybody, Augie Kennedy here, and welcome back to Super Awesome Calculus. We're finishing up Chapter 4 today, entitled Everything is Derivative, and today we're going to talk about the concept of antiderivatives. But before we do that, we're going to go over the optimization problem that I assigned in the last lecture. So, here's the problem, just to refresh your memory. I asked you to consider the following problem. A farmer with 750 feet of fencing wants to enclose a rectangular area and then divide it into 4 pens with fencing parallel to one side of the rectangle. What is the largest possible total area of the 4 pens? Alright, now this was a classic optimization problem that wasn't too different from the optimization problem or exercise that I worked through in the last lecture. The first step, as you know, is to understand what you have. You know that the farmer has 750 feet of fencing. And we want to know max area. So just like last time, we have feet of fencing, that sounds like a perimeter parameter, and we have area as the thing that we need to find. Well, the first thing to do, as I mentioned, is to draw this out. So it's a rectangular area. So let's draw a rectangular area. There we go. Boom. Rectangular. And then he wants to divide it into 4 pens with fencing parallel to one side of the rectangle. You could draw it this way, across. I'm just going to draw vertically. Let's do 1, 2, 3, and pretend those are equal. So here's pen 1, pen 2, pen 3, and pen 4. Now, what is the largest total area of the 2 pens? Well, we don't know that. But we know that in general, we can call this X, we can call this Y, you could call that Z and Q, it doesn't matter as long as they're 2 different measurements. So, we want to find A equals XY. Well, we don't have that. But what do we have? We do have perimeter. Because 750, the amount of fencing that he has to use, is going to equal the sides, the sum of all the sides. So that's 2y plus 1, 2, 3, 4, 5x. And now we've got something we can use. So let me erase some of this, and we'll start working with that equation. Remember, we want to find A equals XY. But we know now that 750 equals 5x plus 2y. Now, if you remember, the step that comes now is that I asked you to isolate y, to put y explicitly in terms of x. So we can only work with one variable. Well, the way you do that is you'd set it up such that 750 minus 5x over 2 equals y. Just isolate that y. Another way to write that would be 375 minus 5 halves x equals y. Okay? You with me? I hope so. So now we have x, and we know what y is in terms of x. So if area equals x times y, another way to say that is area equals x times y is 375 minus 5 halves x. Now we can work with this, because now we have one variable. Alright, so what are we going to do with our one variable? It's pretty simple. We're going to distribute this through. A equals 375x minus 5 halves x. That's area. And we'll call this A as a function of x, because that's basically what it is at this point. Okay, so that's our function. That's our area function. Great. So what do? Remember, optimization means take a derivative. We want the maximum or the minimum. In this case, we want the maximum. So let's take the derivative of this function. A prime x equals 375. Oh, this is going to be x squared. I'm sorry, we had x times 375 minus 5 halves x. Distributing the x through is going to give us x squared. Using the power rule, 2 times negative 5 halves is negative 10 halves, or 5, minus 5x. Now we're going to set this equal to 0, because that's how we find the critical numbers. 375 minus 5x. And we can realize, with very, very little work, that x equals 75. Okay, now, we can eyeball this to find out if we found the minimum or the maximum by looking at the second derivative. Negative 5x, we know the second derivative of this function. The 375 is going to go away, and the x is going to go away, giving us negative 5, which is always negative. And if you remember the second derivative test, if it's negative, it's going to be concave down, which means we found a maximum. So x is indeed the maximum, but we're not done. That's the maximum, but we need to plug this back in to the original function, a of x. And if we do that, you'll find, with your calculator or with a lot of computation, you'll find that a of 75 equals 14,062.5 feet squared. That many square feet. And that is the maximum area. Now, that's optimization. Today we're going over antiderivatives. And after optimization and all of those graphing rules and L'Hopital's rule, this is comparably much easier. So, the idea of the antiderivative is very similar to the idea of the inverse function. If you remember in the past, we asked questions of how can you find the inverse of a function in order to undo it. For instance, what happens if you have sine x equals like 7? Well, how do we get rid of that sine x? How do we isolate it? Well, we took what was called the arc sine. So sine equals arc sine 7. Oftentimes, to isolate the variable, we'll do things like dividing and multiplying regular algebraic operations. We know the inverse of e to the x equals ln x. But we also discussed, at the end of chapter 2, the idea of the derivative as a function. So if the derivative has a function, could it have an inverse? And the answer is basically yes. Yes, it can, and yes, it does. And this inverse is known as an antiderivative. Okay? Now we're going to be dealing mostly with elementary functions here. So most functions that we're going to be looking at are going to have pretty easy to find antiderivatives. Now, what is an antiderivative? Let's say we have f of x equals x squared. We know that the derivative, f prime x, is 2x. But what if we're given this? What if we are given information that f prime x equals 2x plus 3? And someone asks us, what's f of x? Well, what we do then is we take an antiderivative. And the way we write that is we write f, big F, and big F prime x is equal to f of x, supposedly. The big F is called the antiderivative. Alright? So, let's say we have f of x, right here, is 2x plus 3. And we want to find f, big F, antiderivative of x. Well, we know that the antiderivative, the thing that you take the derivative of to get 2x is x squared. And we know that the way you get 3 is taking, the way you get a constant is by taking that constant with an x in front of it. So, the answer is x squared plus 3x. And you can check this. The derivative of the antiderivative is 2x plus 3. Okay? So that's the idea of antidifferentiation. It's basically taking the derivative in reverse. So remembering all of your power rules, all of your various rules, this is a way that you can undo everything. And this is very important when we get into talking about integrals. So here are some functions that have what's called an antiderivative. It's important to note that if you have a function like this, like what we talked about before, f of x equals 2x plus 3, and we want to find f of x, it's important to note that in doing this, we know that's going to be x squared plus 3x, but, I mean, what if this is plus 7? Okay? The derivative of the antiderivative is going to be 2x plus 3, but what if it's 48? Well, the antiderivative's derivative is going to be 2x plus 3. So really, at the end of every antiderivative, you have to make that allowance, that there's going to be some constant that's going to be a little bit different. Every time you take an antiderivative, you're going to be introducing a new constant. So if you have to take two antiderivatives, you're going to have two constants. We'll see how that works in a moment. So plus c is how you write it. And in general, that's the way it's written. F prime x plus c is the antiderivative. Now, I'm going to give you a few antiderivatives that you'll probably know. If we have a function, c, a constant times a function, the antiderivative is going to be c times the antiderivative. Pretty easy. If we have f of x plus g of x, the antiderivative is going to be big F of x plus big G of x. The sum of the derivatives is also going to be the sum of the antiderivatives. Now, regarding this, x to the n, that's the power rule. Remember before we took nx to the n minus 1. Well, now we're doing the exact opposite. Now we're raising the power of n. So we get x to the n plus 1 over n plus 1. This is a very important one that you'll want to get to know pretty well. So something like x cubed is going to be x to the n plus 1, x to the fourth, over n plus 1. 3 plus 1 is 4. And you can check that. You can see that that would be 4x cubed over 4, or x cubed. So that's the way that the new power rule for antiderivatives works. Alright, moving on. A few other important antiderivatives that you'll see. Oh, by the way, remember all of these are plus c in the antiderivative case. So right here, we know this one. F of x equals 1 over x. Well, what function gives us that as the derivative? We know that that is the natural log of x. Except it could be the natural log of either the positive or the negative, so we call this the natural log of the absolute value of x plus c. Alright? Just remember, there's always going to be a plus c in there. Now, we've got this special case. If f of x is e to the x, well, you might have assumed already, and correctly, that the antiderivative is also going to be e to the x. Cosine of x, what function taking the derivative gives us cosine? We know that that's sine of x. And we know that sine of x, well, we know that the derivative of cosine is negative sine x, so the derivative of negative cosine x should be sine x, and in fact it is. That's the antiderivative for sine x. Then you'll get a few others. These are actually ones that we'll be starting to look at. We'll look at a lot more trigonometric functions. We've got secant squared x, the derivative. If that's the derivative, what's the original function? That's tangent of x. We've got 1 over 1 plus x squared. We might remember that as the arctan of x. That's the derivative of the inverse tangent. So those are some basic antiderivatives. Now let's see how this works. Well, we can get something like this. We want to find f. Okay, our goal is to find f. And what we're given the derivative. F prime of x equals e to the x plus 20 times 1 plus x squared to the negative 1. And we know that f of 0 is negative 2. Okay, so first thing we're going to do is we're going to rewrite this function. We're going to write f prime x equals e to the x plus 1 plus x squared to the negative 1 is just going to be 20 over that quantity. Because anytime you take something to the negative 1 power, you're putting it in the denominator. So 20 over 1 plus x squared, and that's our derivative. And we know f of 0 is negative 2. That's a 2. Okay, well, looking at this, we're going to find big F, or, regular, okay. Well, we know that this is f prime x, so I can just write little f of x, and we can understand we're going from the derivative to the real function, to the original function. Well, what do we see? We know that the antiderivative of e to the x, the way you get e to the x is with e to the x. But now look at this. Sum to 20 over 1 plus x squared. Well, we just saw that. 1 over 1 plus x squared, the way you get to that function as a derivative is through arctangent. So we have 20 times 1 over 1 plus x squared, or 20 arctangent, tan to the negative 1, plus c. Right, plus c. Now, f of 0 we know is negative 2, so let's plug in 0. F of 0 equals negative 2 equals e to the 0th, which is 1, plus the tangent of 0 times 20 is going to be 0. Well, that means, plus c, that means that c is going to equal negative 3. And sure enough, our final function, f of x equals e to the x plus 20 arctan x plus, or minus 3. And that's how we do antiderivatives. Now, sometimes, like I mentioned, you'll need to do an antiderivative more than once. Here's a pretty good example of that. I'm going to actually have to make this one up. F double prime of x equals, I'm trying to think of the easiest one to do here. It escapes me. So let's do f double prime of x equals 6x cubed plus 3x squared plus x. Okay? Well, f prime of x, we're going to use the power rule here. It's going to be 6 to the x to the 4th over 4 plus 3x cubed over 3, okay, plus x squared over 2 plus c. All right, we can just call 3x cubed over 3 x cubed. Now, that's only the first derivative. We want to find the original f. Well, the way we do that, we're going to take the antiderivative of all of that. And that's going to give us 6x to the 5th over 4 times x. What am I doing here? Or 20 plus x to the 4th over 4. Wait, let's see. 30 over 20 is going, yeah, that works. Plus x cubed over 2 times 6 plus c. But you see that c, when we raise it up a power, is going to take on an x. And we're going to have a new variable, a d. Because whatever number that was, if it were 7 or 20, the point here is that if that c were 7 or 20 or no matter what, when we take the antiderivative, the only way that that number could have been there is if it had a variable. So we have to put an x there, plus d, and we introduce a new letter. That's the way that you might end up with several different letters here. Now, the last thing that I want to cover on antiderivatives is a practical application to physics, for instance. All right, sometimes you might know, if you've taken physics before, that you have the position function, s of t, is position. The derivative of s of t is v of t, the velocity function. And v prime t equals a of t, the acceleration function. Okay? So what we can do is we can be given, let's look at this. Here's a good one. A particle moves in a straight line and has acceleration a of t equals 6t plus 4. Its initial velocity, v of 0, is -6 centimeters per second. And its initial displacement, s of 0, equals 9 centimeters. And we want to find s of t. Well, we know a of t is the second derivative. So we're going to take the antiderivative of a of t, which will give us v of t. That gives us 6t squared over 2, or 3t squared, plus 4t, plus c. But we know that v of 0 is -6. So v of 0 is going to be 0 plus 0 is going to have to equal -6. So c must be -6. That means that we have 3t squared plus 4t minus 6. Now we take the antiderivative of that to get the position function. S of t is going to equal 3t cubed over 3, or, very simply put, t cubed, plus 4t squared over 2, or, very simply, 2t squared, minus 6t plus c, or we can call it d, we call the last one c. Alright, and now we know that s of 0 is going to equal 9 centimeters, so we have s of 0 equals 0 plus 0 minus 6 plus 9 equals d. Well, equals d. So we know, therefore, that d must be 9, which means that our position function is this. That's how we get from acceleration to velocity to position. And that is what you need to know about antidifferentiation for right now. There's going to be much, much, much more of it for the rest of the course, as this is we're leading into integrals now. We have a test next time, but in the meantime, I've got one more big problem for you from this chapter. It's computational, and it's just going to give you some practice using antiderivatives. Here's the question. F double prime, the second derivative of x, equals 24x squared plus 2x plus 10. If you know that f of 1 is 5, and f prime 1, or f prime of 1 is -3, find f. So here you're given the second derivative, and you're given initial conditions of the first derivative and the initial function. You should be able to find the specific solution for this function. All right, well, we'll go over it next time, and in the meantime, thank you very much for joining Super Awesome Calculus, and take care, y'all.